Hi everybody, in this video we are going to graph the more wild and crazy rational functions, not the very basic transformations of reciprocal functions. So we're going to have more than one asymptote in the vertical direction, and our horizontal asymptote might not be horizontal at all. It might be slanted, could be quadratic, it could be any type of oblique asymptote. So I'm going to break this into categories. So right now I'm going to focus on the examples where the m is equal to n. What do I mean by that? If you look, let's see what I could do here. If you look at my arrow, this is the setup of a polynomial over another polynomial, and that's what I mean when I'm talking about a rational function. It's the ratio of two polynomial functions. Ax to the m represents the leading term of the polynomial in the numerator, and bx to the n represents the leading term of the polynomial in the denominator. So we're going to pretend that they're nicely done for us in standard form. M and n, when the powers are the same, that's going to be the examples I'm going to talk about in this video. I'm going to break it into three situations: one where they're equal, one where m is less than n, and the third one, for now, very simply, when m is greater than n, but by varying degrees has different results. So let's get started. Now, before I put away the little arrow, here is my beautiful chart of how everything works. All right, so let's just hide that a bit. Okay, so here in this chart, the numerator, if you take your numerator of your rational function and put it into factored form, you set y equal to 0. When you want to know when a fraction equals 0, y equals 0, you want to know basically when the numerator equals 0. Why would we want to know when y equals 0? Well, y equals 0 on the x-axis. So, therefore, by setting your numerator equal to 0 and solving by factoring the zero product property, you will find your x-intercept. So, again, factor your numerator, set each factor equal to 0, that's the zero product property, you're going to get your x-intercepts. I'll elaborate on the behavior of each x-intercept in a moment. Next, how do I get the y-intercept? I fill in 0 for x, but when I do that, a shortcut would be to look at the right side of the fraction. So the numerator, oops, didn't mean to mess with that. The numerator, I don't want to move that, stop, give me the arrow. The numerator, purple, this line represents dealing with the numerator. The green represents the right side. And what do I mean by that? In expanded form, the ratio of constant terms is the y-intercept. So if I fill in 0 for x, similar to how I filled in 0 for y, I will get the y-intercept. All the terms that are not constants, that are having a variable in them, vary versus constant, right? So all the variable terms are going to be turning into 0, so you'll be left with constant over constant. That will be your y-intercept. But what if it's not in expanded form? 0, or what else could happen? If you get 0 over a number, just keep in mind that that is equal to 0, and 0 can be your y-intercept. In that case, it would probably be your x-intercept as well. If you get a number over 0, what does that tell you about your y-intercept? In this case, x equals 0, aka the x-axis, overlaps a vertical asymptote. So your x-intercept is overlapping a vertical asymptote, so the vertical asymptote wins. Like in rock, paper, scissors, it would win. Okay, next, set the denominator equal to 0. So we're going to do the same thing we did in the numerator with the denominator. What do you remember from Algebra 2? Well, hopefully you found restrictions in rational expressions, and you found restrictions by finding what values would make your denominator equal 0. Those restrictions in a graph cause vertical asymptotes. That's where your fraction is undefined. And like graphing trig, where it's undefined, we have a vertical asymptote on our graph. We'll elaborate on that behavior as well in a moment. And now in blue, we're looking at the left side. We're looking at the end behavior, which most people call your horizontal asymptote, but it really is just your end behavior. Sometimes it looks like a horizontal asymptote. In expanded form, the ratio of the leading terms decides the end behavior. Like I said, often called the horizontal asymptote when dealing with rational functions. The leading terms ratio, so you have ax to the m over bx to the n, If the powers are, we're going to focus today on when m is equal to n, it's a over b. Now, why is that? If you're finding end behavior, you're filling in either infinity or negative infinity conceptually for your x value. If you're filling in something infinite in for your x value, that basically means that your leading terms matter the most. So if they matter the most, these terms right there, if they matter the most, I mean significantly so, the bigger the thing you're plugging in gets, the more they matter, then you could ignore the rest of this. So if the powers are the same, x to the 2, x to the 2, you could basically reduce it out, and all that's left is the ratio of a over b. So if they're both 1, then you draw a horizontal asymptote at 1, and that is your end behavior. Your graph is going to go towards 1. If it's 2 over 1 or 12 over 3, whatever it is, that ratio, that constant number, when in this situation, will be our horizontal asymptote. Now for the x-intercepts, the factor that it comes from dictates the specific behavior locally at the x-intercept. If the factor, most commonly, is to the first power, it's going to slice straight through the x-axis, pretty straight, like a linear equation. Excuse me. If it's going to be a factor to the second power, then it's going to behave like a quadratic locally. Overall, no, but locally, yes. And then third power, it's going to look a bit like a cubic. Basically, anything even power will kind of look like this, and anything odd powers third or bigger will kind of look like this. Similar to end behavior of polynomials, your vertical asymptotes can behave a certain way as well. If the factor your vertical asymptote came from had an even multiplicity, then both branches will be pointing up or both branches will be pointing down. All of this information is going to be dependent upon how all the pieces work together. And when your factor that you got your vertical asymptote to is to an odd multiplicity, then the branches are going to point in opposite directions. One is up and one is down. So we're going to tie all of this together in a couple examples now. Now, if you don't know how to factor, I am not teaching you how to factor in this video. So that is something you have to do separately on your own time. Sorry, I just don't have time right now. Here, what form is this given to us in? We have 2x squared plus 3x minus 20 over x squared minus 3x minus 10. I would say that this over here is in expanded form. What's up, bud? Dallas says hi. Who's that on the screen? You're being shy? You wanted to come up here. Say hi. You don't care. That's expanded form. So the other form, which I'll find useful, will be factored form. If I factor the numerator with the AC method and grouping, or in my brain, I will get 2x x. Now to get a 3 in the middle, that means I would have an 8 and a 5, positive 8, negative 5, positive 8, so plus 4 here gives me outer as positive 8x, minus 5 right over here gives me negative 5x in the middle, and then the bottom 10. So I have x and x. I'm going to use 5 and 2 to multiply to give me my last times last is 10, but I need negative 3 in the middle, so that's a negative 5 and positive 2. All right, there's my factored form. Done. Almost there. Almost there. Now I'm going to use the same color coding as here. Okay? So the first thing I'm going to find are my x-intercepts, so I'm going to use purple. X-intercepts. Can you read that? No, because it looks like garbage. Forgive me. X-intercepts. So what did the directions say to do? They said to factor and then solve, setting the numerator equal to 0. We're using zero product property. What do I get? 2x is 5. X equals 5 over 2, which we should know is 2.5. And x equals negative 4. So here's negative 4. Here is 2.5 right there. Negative 4, 2.5. Now, the parentheses that they came from were both to the first power. So they will behave like linear equations at those places. So when I end up drawing everything, I'm going to slice more or less straight through, but I'll get there when I get there. Next is the y-intercept. Now what color? Green. So grabbing the green. What's up, bud? You want to do the math too? You do? That's amazing. Why are you so smart? Such an ambitious young gentleman. All right. Here you go, bud. I know. You could lay on this arm. All right. Y-intercept. So I'm going to go back to the more or less the expanded form. Forget which marker was better. If I look at expanded form, what my little graphic organizer wants us to do is basically look at the right side, the constant over the constant. I have negative 20 over negative 10. Negative 20 over negative 10. So what is my y-intercept? That's going to be 0, comma, negative over negative is positive, 2. 0, comma, 2, right there, 2, y-intercept. That's it. Ready to go. Next are the vertical asymptotes. I don't know if this is gonna, do I regret my decision? Not really. Okay, there's the top. I mean, it's not great, it's not horrible. So what color did I use for my pink? Pink. So where do I look for that? Denominator. Right here. So how do I do vertical asymptotes? I solve the same way. X plus 2 equals 0. So x equals negative 2. And x minus 5 equals 0. X equals 5. So 3, 4, 5. And let's see, I'll label 5. Now again, these are also to the first power. So somewhere over here, I'm going to label odd and the 5. And then the other one I wanted was negative 2. And that is odd as well. All right, and what else do we got? The last thing we have is our horizontal asymptotes, and I think I did blue for that. Horizontal asymptotes, and in this case, my m and n are equal. You look at your leading terms in expanded form. So you see we looked at the top, we looked at the bottom in factored form. We kind of look at the x stuff in factored form. So if you think of the show X Factor, so we looked at the x-intercepts and the vertical asymptotes, which are both x stuff. And then y stuff we look at in expanded form. All right. So I'm doing this guy right here. Now what does the rule say? We just saw it on the screen a little while ago. When m equals n, it's the ratio of the leading coefficients. So if you wanted to show some work of some sort, LT over LT, leading term over leading term. Just for now, this is really more of a limit, but I'm just keeping it light right now. 2x squared over x squared, which is really 2. So y equals 2 is my end behavior. Now, 9 times out of 10 or more than that, your teacher is going to draw the horizontal asymptote all the way across. Personally, I like only drawing it at the ends, but you know, is what it is. Got to play by everyone else's rules sometimes, because it is end behavior and you can cross a horizontal asymptote in the middle versus a vertical asymptote, which you could never cross anytime, anywhere, ever. So the horizontal asymptote is more about like what's happening way out there. What's the trend? What are we going to fall in line with? Now, hardest part, putting this all together. For one thing, I know that these two are going to connect. They're between these two asymptotes. They have to connect to each other some way, somehow. I know this x-intercept behaves like a linear, so that means I'm going to go right through my x-axis, pretty straight, you know. Of course, it's all based on everything else around it, what looks straight and what looks curved, but there you go. And I'm going to approach this asymptote and go down forever and ever. I can't come back up because I don't have another x-intercept between here and the asymptote. Here, I have to go up forever. Another way I know I'm never coming down is, again, I have no x-intercept here. Now, odd power on my vertical asymptote means if this side of the asymptote is pointing up, then this side of the asymptote must be pointing down. Definitely going to connect to that x-intercept. It should cut through pretty straight, and then it should approach the end behavior. All right. Here, again, odd. So if this side's pointing down, then that side is pointing up. And I have no reason to go visit my x-axis, no x-intercept, so I'm going to stay in that little corner, and there I go. Beautiful. I mean, not the best drawing I ever did in my life, but not terrible. Domain, what x values are being used? From negative infinity until -2. -2 is not being used at all because there's an asymptote there. U for union, and then from -2 until 5, we're good. We're using all these x values in here. Union, and then from 5 to infinity. Okay? As for the range, it goes from bottom to top, and I have this piece which is smooth all the way through. So actually, my range is going to be, because of that little squiggle, negative infinity to infinity. The range is hard to do sometimes, and you need calculus, but not all of the time. So that was just one example. I will do other examples where m is equal to n, but in a nutshell, that's just one case. Look for others. I'll call them chapter 18, part 2, part 3, part 4. Okay, so I'll do another one. Chapter 19 will be probably when m is less than n. I'll focus on those because those are what you see the most in the beginning. Thumbs up, thumbs down, comment, question, concern. There's more videos of me graphing rational functions on my playlist or in my video archive, so go search the word rational on my channel, graphing rational, something like that, and you should be able to find something pretty good. Dallas says, I'm waking him up. Oh, he hates me. Dallas says, graph hard, study hard, so you can be smart like him. Right, Bubba? I know. Okay, nap time again. All right, adios. Thumbs up for Dal. Paws up.